Yes, Test 2022, 23. Okay. Should we start? Hello. Is the microphone on? Yes. Hello. Welcome to today's session. My name is Ulrike Heiter. I'm from Uppsala University in Sweden, and I will chair this session, which will be about stellar chemical composition mainly, but there will also be a few talks about circumstellar disks. But we start with an overview talk by Elisa Delgado Mena from Madrid about the impact of stellar composition from galactic chemical evolution to planet formation.
Hello everybody, good morning. First I would like to thank the organizers for inviting me to give this talk. And as Ulrich said, I'm going to talk about stellar abundances and how they can impact the studies we do over a variety of topics that I will mention. So first I will explain why stellar abundances are important. Then I will give some brief summary of how we get abundances from stellar spectra. And then I will mention some results on the star-planet connection for FGK stars, and also about chemical abundances in M dwarfs and the challenges that we are facing with those complicated stars. So first of all, why stellar abundances are important? Well, the chemical abundances from stars are used in a wide variety of topics. So they serve to understand the formation in the galaxy, and to understand also all the nucleosynthesis processes that are happening there, to understand how the elements are formed and in which places in the galaxy. So all this leads to what we generally call the galactic chemical evolution. And also it's important to know the chemical abundances to understand the populations within the galaxy and to classify them in the thin and thick disks, for example, or also to apply chemical tagging, which is a technique to compare the abundances of stars and assign populations within the galaxy, like open clusters, for example. Then the chemical abundances can also help us to better understand asteroseismology and stellar activity to complement these studies, and also they can help in the determination of distances and ages. And finally, and most importantly for this conference, chemical abundances are necessary and help in the detection and characterization of exoplanets. So in this talk, I will focus in these two topics, and I will start first by the galactic chemical evolution. So it's important to know the chemical abundances at different scales to understand how the elements were formed in the universe and what were the steps that happen in between. Here, I just show a brief comparison between the composition in the universe, which is mainly hydrogen and helium, and the composition of the Earth's crust, that you can see it's very different. So how we have passed from one to the other? Well, this is what galactic chemical evolution tries to understand, and all started in the Big Bang with the primordial nucleosynthesis. So in the very first seconds and minutes after the Big Bang, all the helium of the universe was created, and also some traces of lithium. So the initial universe was mainly hydrogen, helium, and these traces of deuterium and lithium. So where do the rest of the elements come from? The answer is in the stars through stellar nucleosynthesis. So the first stars in the universe were the population 3 stars that we cannot observe nowadays, but these were supermassive stars that have very short lifetime, and they release in the universe the first metals. After this, next generations of stars, through stellar nucleosynthesis in different ways that I will mention now, created the elements that we have now in the planetary systems. This table that probably many of you know, it's a very nice summary of the production sites for different elements in the universe. But to reach to this, a lot of studies were done studying different populations of stars to understand how these elements are formed. So in the 90s, there were starting to be more surveys with high-resolution spectroscopy, and then we were able to determine abundances in larger samples of stars, like this one, this seminal work by Edwardson et al. In 1993, where they were already analyzing 200 FG stars in the disk. And here it was already shown how the alpha over iron abundances increase towards lower metallicities, and then they started to see this different behavior. That later, with later studies, it was shown that it was the difference between the thick and the thin disk. As the time passed and we have more instruments and bigger samples, then we could start to better trace these populations. And for example, in this work by Adi Bekianeton in 2011 with the HARP CTO sample that I will talk later more about, with more precise abundances, we couldn't distinguish the thick and the thin disk, but also it was discovered another population of high alpha metal rich stars, which it's not clear whether this is a thick disk extension of towards higher metallicity, or it's a different population. So as I said, there are different stellar nucleosynthesis processes happening in different stars, and this gives origin to different elements. So first we have the massive stars evolution, that as they reach to the end of their lives, they have a lot of layers with different elements, and with these stars explode as supernova type 2, they release all these elements to the interstellar medium. So these are the main producers of alpha elements. So this is magnesium, silicon, titanium, and other elements later than that. However, the iron peak elements, iron and iron peak elements like nickel, cobalt, and manganese are mainly produced in supernova type 1a. And these are explosions that happen in binary systems of lower mass stars. And that's why we see a difference between these two kinds of elements. That coming again to the previous plot, so this is what produces this knee here. Because the elements released by massive stars go to the galaxy before, at earlier times, because the massive stars die earlier, then the alpha elements are released in the interstellar medium before than the iron peak elements, with more or less a 1 gigayear delay. And this produces this knee, where the production of alpha elements is balanced with the production of iron around solar metallicity. And all this we know because we were studying stars for a long time, and different populations of stars in the galaxy. So if, together with the chemical abundances, we add the stellar ages, then this is what we call galactic archaeology, as a very broad topic. This opens the door to a more insightful view of all these populations and to understand how the stars form in different environments. So in the last years, there have been a lot of many large surveys that I mentioned here, like LAMOST, APOGEE, GALA, Kepler, Gaia ISO survey. All these surveys have a big amounts of stars and in different positions in the galaxy, because then, of course, they go farther than the solar neighborhood. And with all of these surveys and previous works, we were able to understand how all these elements form. So not only the alpha elements and the iron peak elements, but also we were able to study the air process elements or heavier elements that are produced in different kinds of stars. These works are very important because we have large statistics, because the number of stars is huge, millions of stars we have. However, the problem of some of these surveys is that they are limited somehow because the resolution is lower, and then we have a large number of stars, but we don't have very high precision abundances. So for this, it's also important to keep studying the solar neighborhood with high resolution and high signal-to-noise data. And this is what we have been doing in our team for a long time, using the HARP CTO sample, which is a volume-limited sample in the solar neighborhood, around 70 parsecs around the sun, and it has a bit more than 1,000 stars. And then we were able to distinguish different populations, as I said, especially this one that hasn't been seen before, the high alpha metal rich stars. So these are stars that have a similar metallicity as the thin disk, but they are a bit enhanced in alpha abundances, and there is a gap between these two populations. And it's also important to note here that some studies decide to make this distinction between the thick and the thin disk using kinematics, and others use chemical abundances, others use a mix of both. So in our case, we have been using the chemical separation to make the distinction of our abundances. Later, we were able also to study in this sample the heavy element abundances, as in this plot I'm showing. And we were also able to show for the first time that zinc, for example, is also very well separated. The zinc abundances are also very well separated between the thick and the thin disk. And also europium is very well separated, not as, of course, because the errors are larger, it's not as clear as for the other alpha elements, for the alpha elements, but we can see that the abundances are also enhanced. And in some of the elements, we can also see the different behavior for these high alpha metal-rich stars. So again, this was possible because for this sample, we have very high precision in the abundances, and we are able to see these differences. So these heavy elements that maybe you haven't heard much about them, but they are important, especially now for the ages, as I will explain a bit later. These heavier elements are created in the late phases of AGV evolution, so when the thermal pulses take place, through neutron capture, and then you can create all these elements that are like strontium, yttrium, zirconium, barium. And then in the case of rapid process elements like europium, they take place in explosive nucleosynthesis in the supernova type 2 explosions. But also in the last years with new studies from LIGO, they have proved that probably these elements can also be formed in neutron star collisions or mergers, which releases not only these kind of elements, but also other very heavy elements like thorium, uranium, and more exotic elements like golden or silver. So together, as I said before, the H's are very important, not only the abundances, because all together serve us to trace how these elements were formed through the time of the galaxy formation and evolution, and also to understand later, as we will see, where the planets are formed, because at the end the planets are imprinted by the composition of the original protoplanetary cloud. And this comes from what will happen before in the surroundings of these stars. So in this plot, I'm showing the alpha over iron versus metallicity with a color range for the H's. So these are the thick disk stars that have old H's, like above 12 gigayears. These H's come from isochrons, so of course they are not as good as if we were having asteroseismology, but this is the best we could have for this sample. And then you can see here these high alpha metal-rich stars that are the squares, which have older H's than the thin disk stars at the same population, at the same metallicity, sorry. And it's very clear the gradient in color. So the younger stars in the thin disk have lower alpha abundances and they grow in age. For a fixed metallicity, they also have a higher alpha abundance. This can also be seen with these other elements that I'm showing here, like aluminum, copper, or zinc. You can also see this gradient in age that is better seen in some elements like zinc compared to others. But then, because of the time delays in these different chemical abundances, we can do abundance ratios of different elements, especially those that are produced by low mass stars and those that are produced by massive stars. And then this can serve as tracers of age. These are called chemical clocks that maybe you have heard about them, like yttrium, magnesium. I'm not showing them here, but just to show the relation of some of these elements with the age. So some of them have very strong correlations. But also, you have to take into consideration the metallicity. So the trends are not the same for stars of different metallicities that you can see here. So if you combine some of these abundance ratios, then you can have a proxy for the age with these chemical clocks. In the solar neighborhood, they work quite well, but then you have to be careful when you go outside because there is also a dependence on the galactocentric radius. So depending in which part of the galaxy you are, they cannot work as well, and you have to consider this into account. Okay, so now that we know more or less how these elements are formed, now let's pass to the part more related to planet formation. So as I said, the planets form in the same cloud as the stars. So it's logical to think that, in principle, they should share a common origin in the abundances, right? So since the earlier studies, and since the first planets were discovered, and we were having small samples of 10, 15 planets, it was soon seen that there was a giant metallicity correlation that probably all of you know. This was the first paper by Gonzalez in 1997. And then as the samples grow, then it was seen that the cause for this metallicity enrichment in stars hosting giant planets was primordial. So that is, you need to have a given quantity of metals in order to produce giant planets. Then, as the instruments improve, we were able to discover not only giant planets, but also smaller sized planets like super-Earths or Neptune-sized planets. And most of the studies working with these stars show that the correlation that we see for giants doesn't hold for lower mass planets. So for example, in this one with Kepler data, you see that the distribution of the metallicities of the stars hosting smaller planets is similar to the field stars. Or like in this paper by Sousa in 2018, the distribution of the Jupiter hosts has a larger metallicity than the Neptunians and the field stars, but there is no difference between these two populations. In any case, we still don't have a lot of stars with good metallicities and small planets, so I guess this will be revised in the future as more and more smaller planets are discovered. So once we were knowing about iron, then we say, okay, and what happens with the other elements? So the first studies had some limitations because the samples were small, then they were taken, the abundances were heterogeneous, and the comparison samples that they were using were not appropriate because they were using single stars as comparison, and then you didn't know if there were planets or not there. So we could start to see real separations and significant differences with the HARP CTO sample because we have a comparison sample of stars that we know for sure that they don't host giant planets up to a given distance. And then we saw this increase in the alpha over iron abundances for planet hosts. So the red points are Jupiters and the triangles are Neptunian-sized planets. And as you can see, this is probably a hint that, okay, if you don't have enough metallicity, if you don't have enough iron, then you need other elements to form planets. This can be compensated somehow by alpha elements like silicon, magnesium, or oxygen that we know that are important for planet formation or for interior composition of exoplanets. So having these abundances is important not only to know the star, but also to understand the interior composition of rocky exoplanets. Because if you have the mass and the radius and you have the densities, there is a big degeneracy between the models. And then having the stellar abundances can help constrain the interior composition of these exoplanets. Some of the first works on this topic was made by Bonnerot in 2010, where they were using dynamical and chemical embodied simulations to create planetary embryos using stellar abundances as an input information. And then they were determining the bulk composition of these exoplanets, and they show that there is a large variety of compositions that you can see depending on the composition of the star, like this sample shown here. But okay, I'm not going to talk more about this because this will be better, it will be further explained in the sessions tomorrow. So now that I have explained a bit the importance of the abundances, I will explain more or less how we derive these abundances with some examples. So the first thing you need, of course, is a stellar spectra, and the higher the resolution and the higher the signal to noise, the better, to try to find especially some elements that have very weak lines, and you need to have this good spectra. Then you need a model atmosphere. I cite here some of the most used in the literature, like Atlas marks of Venice. Then you need a good line list of atomic data for your lines. So you need either atomic or molecular lines, and there are some databases online that you can use, like BALT or NIST. And finally, you need, and most important, a radiative transfer code, like MOOC, TurboSpectrum, Venice, etc. And with all these tools, with all these ingredients, then you can do your analysis. In our studies, for example, we have applied 1D LTE, so we are not considering 3D atmospheres, and we are considering local thermodynamic equilibrium. But then these effects are also important, and many works are studying these effects, especially of the 3D and LTE abundances, the 3D and LTE effects in larger populations of stars now that these models have been implemented for a larger number of lines, because at the beginning very few lines have been detailed. It's a very long work that takes a long time to be implemented. So to derive these abundances, there are like two classical methods. One is the equivalent width method, which applies the curve of growth to determine the abundances, and the other one is the spectral synthesis. So for the first one, you need to have isolated lines or lines that can be well deblended. So here I'm showing an example of carbon atomic lines that have been used widely in the literature, this one and this one. They are not very strong. So for example, in the sun, they are just 30 and 19 milliangstroms. But then, for example, if you have a lower resolution spectra, then you will not be able to deblend these 3 lines, and then you will not be able to measure carbon. This is another example of a line of yttrium, which is one of these heavy elements that we use to determine H's. In this case, the lines are stronger. But then, for example, if you have a fast rotator star or a lower resolution spectra, these 2 lines will be blended in one. And then you cannot measure the equivalent width as well as if they are separated, and then it's better to perform synthesis, as I will explain now. Here I also show some example of barium lines that are much stronger lines. More than 100 milliangstrom in a solar analog. In this case, for example, for these lines, you have to be careful because they have hyperfine splitting, so it's not a single line, it's composed of a lot of individual lines that merge together. And then for the spectral synthesis, in this case, instead of just modeling one line, then you can model different regions in the spectra and then compare your spectra with these models in the lines where you are interested to measure. And this method is better used when you have lines that are blended, like this sulfur line, for example, that you cannot deblend measuring the equivalent width. Or for the case of lithium, for example, that is a doublet and is an asymmetric line, and also you cannot measure the individual equivalent width. And now I will talk a bit about oxygen, because it's a very important element. So this is a very tricky one, because the lines are very weak, and the lines that are strong, like the triplet here at 700 angstrom, is affected by NLT. So there is not a good line for oxygen, and sometimes it's a bit complicated to derive the abundances. So in this spectra that looks very nice, this is the oxygen line. So look how weak it is. It's in the sun is around 3-4 milliangstroms. And it's blended also with nickel, so you have to consider this blend. But to reach to this signal, we co-added 78 Harps spectra to release a signal to noise of 650. So you need very good spectra to derive these abundances. However, you have to be very careful because this oxygen, well, here, this is just an example of how will be an individual spectra. And then by co-adding all of these ones, you reach to the black one. But you have to be very careful because this oxygen line, there is also an ergolow. So it's a line that is produced in the atmosphere, more or less at the same wavelength. But depending on the radial velocity of your star and the time of the year you are observing, then this peak can be stronger depending also on the atmosphere conditions. So if you don't see this emission line and then you co-add your spectra, then you can end up with a weaker line than in reality, because this is going the opposite way as the line, right? And then you can derive underabundances of oxygen, which can in turn have an effect of other ratios like CO and can have an impact in your results. So you have to be very careful with this line. And not only this ergolow, also in this region there are also tellurics. Here I'm showing an example of a 83 espresso co-added spectra for a K0 star with a signal to noise of 960, so it's very high. And this is the difference between removing the tellurics or not. So the red is the corrected spectrum. And even if this looks small, given the small equivalent width of this line, even this difference can have a large impact in the abundance you measure. Because of this, we have tried to use another line that is at 6,158 angstrom, which is not contaminated by these features, and that is not blended either. The problem is that it's very weak. It's this line here, and you cannot use it for hot stars. And also, if your signal to noise is not good, like these two spectra, for example, then you cannot measure this line. Okay, so now I will just briefly mention some of the results we could find by studying these precise abundances in FGK stars and how it relates, how we can connect the stellar abundances with the presence of exoplanets. So as I mentioned before, the main differences we found was for the alpha elements, but we explored all other elements in the HARP CTO sample, and we were finding also difference in other elements like aluminium or scandium, for example. And not only the refractor, these iron peak and alpha elements we have tested. Well, here you see the individual values of silicon and magnesium and titanium, that the three of these compose the alpha over iron that I showed before. We were also testing the possible differences for other elements, also for the heavier ones. We found differences for zinc and for barium. But of course, not all the differences you find are due to the presence of planets, because some of these elements are not important for planet formation, but just because they share a common origin. So for example, the case of zinc, this behaves similarly as the alpha element, so that's why we see that increase in the abundances for planet hosts. And then, well, there have been, of course, other studies later than ours that have been studied, like the work of Biazzo in 2022 or Sarma in 2024, that you can see for more recent results on this topic. About carbon, which is an element easier to derive than oxygen, the problem is that the lines that we have been using, these atomic lines, cannot be measured in very cool stars, so then we also analyzed this element in the HARP-CTO. And we found also this trend of enhanced abundances towards lower metallicities, but this difference is at the borderline of being significant because we don't have enough stars. As you see in these bins, there is hardly 1 or 2 stars. And in the case of oxygen, we also see this trend, but with the errors in oxygen abundances, of course, it's much more difficult to claim any difference. This has also been observed in other works in the literature. So again, this remarks again this thing that I mentioned before, that when you move to lower metallicities, then planets tend to be forming the thick disk, and probably this is caused by the different chemical composition of these stars. And having these elements, some of them are very important for planetary interiors, like the carbon, oxygen, and magnesium silicon ratios, because these ratios control the distribution of silicates in the rocky composition in the different layers of the stars. And they have been also broadly studied in the literature to see how the stars hosting planets have different values for these ratios. And depending on this, for example, this magnesium silicon ratio, you can see whether you will have planet building blocks that have a higher composition, a higher quantity of pyroxene of olivine, for example. Or if you have very high CO ratios, then you can have planets that are mainly that are called carbon planets because they have a lot of carbon, which is not expected. So these are very rare stars and very rare planets. And just a warning here about the CO ratios, because not only we have the problems in determining the abundances, as I said before, especially for oxygen, but then depending on which lines you use and which models, you can have very large differences. So here I'm showing the CO ratios using this oxygen line at 6,300, the one I showed that can be contaminated, and then the other line that is better. So you see the dispersion, these are the same stars, and measured in the same way. And so for this oxygen line, there is first an effect of the temperature. So the cooler stars have larger CO ratios and a large dispersion compared to this other line. The problem of this line is that you need very high resolution, very high signal-to-noise spectra to be measured. And also we have tested what happens if you apply Atlas or Marx models. And then so the abundances you get from different lines vary slightly. So some lines are more changed than others. And then depending how you do your ratio, you can have a difference between one star and others up to 0.8 index, which is a large difference in the CO ratio. So if you want to compare CO ratios with literature values, and especially to put all of them in the same scale, it's very important to use the same lines, the same models, and the same atomic parameters for your stars and the ones you are comparing with. So since this cannot be done in practice, because of course the other studies use different spectra than you are using and different codes, one way to tackling these systematics is to calculate the CO ratios in a solar spectrum with the same methods you have and with the same lines, and then you can transform these CO ratios with respect to the sun to a common scale, to a common solar abundance that you can take from the literature. And then you are sure that you are putting things in the same scale. Okay, so these previous studies were focusing more on single stars and which difference can we observe between stars with and without planets, but also you can study this in a broader range and try to see how the composition of the stars in different parts of the galaxy can affect the planetary building blocks you will have in different parts of the galaxy and how they can provide different kind of planets. So I think the first work on this was made by Santos et al. In 2017. So we use again these HARP-CTO abundances of iron, magnesium, silicon, carbon, and oxygen to derive core mass fractions and water mass fractions, assuming a very simple model, just with iron in the core and silicates in the mantle. And then we could see that one of the most significant differences was for the thick disk stars, that are the blue ones, and we were seeing that the water mass fraction is much larger in these stars compared to the stars that are in the thin disk. However, for the iron mass fraction is the opposite, and in the thin disk, this fraction is larger. And the difference in the water mass fraction comes mainly because in the thick disk you have larger amounts of oxygen. So then these planetary building blocks will have a different composition in different parts of the galaxy, which can give rise to different kinds of exoplanets. There was a more recent paper on this topic using also abundances, in this case from GALA, and a more complex model considering other compounds, like pyroxene, distinguishing between pyroxene and olivine, for example, and using other components. And then they also studied, in this work by Vitz and Battistini in 2020, they also studied how these planetary building blocks can be different inside and outside of the water ice line. And you can see here, this is the water fraction of planets formed outside of the ice line, and you can see how as the metallicity increases, this water mass fraction is much lower. Then this is compensated as you go for higher metallicities with a higher amount of the magnesium to silicon 04. Of course, there have been a lot of works on this because it's a very interesting topic, and then you can do it either with larger samples of abundances, using also planetary synthesis models. And you can see, for example, these other works that have more recent results on this topic. Okay, and finally about the end dwarfs, because all these correlations we have found are for the FGK stars. But what happens with the EMs? Because now they are the focus of a lot of planetary surveys, because these are the objects where we can find the smallest planets and the planets the closer we know to what we have in our Earth. The problem with the EM dwarfs is that it's very hard to get the abundances and the parameters. In the last years, there have been a lot of studies focusing on these stars, because as I said, this is a hot topic. You need the high resolution spectra, and you have to use near-infrared spectra, because in the optical, these stars have a lot of molecules that erase the continuum, and everything is mixed, so it's a mess to get abundances. You can get parameters, but not abundances. So this was the first work treating with near-infrared spectra in the J band, where you can get the abundances and the parameters from some specific lines. But then there are other bands like the H band that I'm showing here that is severely affected by water bands that depress the continuum. So you can see here the difference between a very cool star with 3000 Kelvin and a hotter star with 3900 Kelvin, the difference in the continuum. So you have to consider this water molecule, these bands that depress the continuum, in order to derive your parameters or your abundances. But fortunately, as I said, now in the last years there have been more and more near-infrared high-resolution spectrographs. And then many studies were able to determine individual abundances. And this is a problem because for the temperature, we are more or less okay. I'm showing here the work by Passenger et al. In 2022, where different teams were analyzing a set of stars using Carmen's spectra with different methods. And then each of these points is a different method. So for the temperature, the differences are not super large. But then for the metallicity, you see the big dispersions. There are differences up to 0.3, 0.4 dex. And then if you cannot fix your metallicity, your iron abundance, then for the abundance of other elements, it will be also impossible. So I'm going to briefly mention some studies with different instruments. For example, this one by Isiwaka with Carmenes and Subaru. They were able to determine several elements in the spectra, and these are the trends they found. So as you can see, the abundances have very large errors. And they were finding that most of the atomic lines are sensitive to changes in abundances, not only of the corresponding elements, but also to other elements, especially for sodium and calcium, for example. Then the team of Soto et al. Have published several works using APOGEE data, which has a medium resolution, not high, 22,000, but still they were able to determine abundances for a lot of elements in end dwarfs that are in binaries as well, to try to calibrate the abundances. And they were able to recover similar abundances to the primaries. You see here another paper using, in this case, Spiru spectra, which is also high resolution. And in this case, I think they were using pre-compute synthetic spectra. And they were finding, so the red is the observed spectra. And there are a lot of lines that are not, that don't have atomic data, and then they are not synthesized in the models. Or this work by Hassi et al. In 2024, using in this case E-greens, another spectrograph, to derive abundances for the planet host K218b, which you can see how the lines can be well synthesized from different elements, titanium, scandium. And finally, I saw here other two recent works using also Carmen's data, this one by Tabernero et al., where they were able to derive magnesium and silicon, but only for stars earlier than M5, because for later types it's impossible. And you see the large dispersion in the abundances compared to the trends in the solar neighborhood, FGK stars. So you cannot see this separation, for example, between the thin and the thick disk. The errors are very large. And this work by Olander et al. In 2025 using Janovi, another high-resolution spectrograph in the near-infrared. In this case, they analyzed 3 elements for a small sample of benchmark M dwarfs, and then they made a comparison with other works in the literature, finding some differences in the trends. So as you see, even if we have advanced a lot with the M dwarfs, it's still not enough compared to the FGK, and I think we are still a bit far from finding these differences, which is a pity because, of course, we have very interesting planets, exoplanets around M dwarfs. So just to leave you with the conclusion, so as you have seen, high precision abundances are possible given that you have very good spectra. Then we have to consider the chemical composition of the protostellar cloud because it conditions the formation of exoplanets. But also the chemical abundances can be affected by planet formation, so the other way around. I didn't talk here about lithium, for example, which is an element that can be affected by the formation of planets or by the engulfment of planets. But this is also interesting to see that there are other abundances that are subject to changes due to the presence of planets. Then, as we have talked also in previous yesterday, so it's very important to have an homogeneous analysis. It's crucial to find significant differences. And finally, for the M dwarfs, we need to improve the models and the line list to be able to reach to better values and more precise values. Okay, thank you.
Okay. Thank you very much. Very nice overview. We have a few minutes for 1 or 2 questions. So please, any questions to Elisa? Yes?
Hi.
Okay.
Very nice talk, Elisa. I was wondering, I saw that there is importance to find very good comparison samples for stars with and without planets. And the HARPS GTO is a very good one. Do you know any other ones that, or how you plan to address this with other RV surveys?
So I'm only aware about the sample from the Keck Hires. I think it's the Spokes sample. I don't remember the name exactly. But this one also, because it was a sample followed with radial velocities, they had a comparison sample. But I really, in that case, I don't know for how long they follow it. So what is the limit of what planets are not in the stars that are considered as single stars? Of course, you never know if there are small planets around these what we call single stars. So we always say without planets or without giant planets, because the only thing we know for sure.
Matthias Amler von Eif, Göttingen. So thank you very much for this great overview. I'm curious about the high alpha metal rich population. Could you please remind me how does it show up as a distinct population, and is it also distinct in terms of kinematics?
Okay, so where was this? Sorry, aquí. Okay. So this was done because the authors did a histogram of the alpha over iron, and they saw that there was a gap in between these 2 populations. And then the kinematics, if I remember well, was in between these 2. Maybe later in the coffee break we can talk, or you can ask the first author that is here. But then, as we analyze more abundances, we saw that not only not only alpha abundances are different, but we also found difference in copper, in zinc, and the H's. So it's still not clear whether this is a continuation of the thick disk. So in some works, they call them thick disk stars at high metallicity. In others, because it's not clear if it's thin or thick disk star. But then, where I have the H's, aquí. So you see here, so meanwhile in the thin disk, you have H's from 0 to 6 or 7 gigayears. Then these stars are more around 10. So there is a difference in the H's as well. So they are older and they are enhanced in alpha elements and other elements, not only alpha. I don't know if it's here. Okay. Yeah. You see also that for the zinc is also enhanced. The yttrium is underabundant compared to the main of the thin disk. And then for other elements, it's more mixed. The barium is also underabundant. The copper is also higher. Yeah.
Okay,
yeah,
so
thank you very much.
Thank you. We have to continue with the next speaker. Thank you again. And now we will hear from Edita Stonkute from Vilnius about the chemical signatures of planet-hosting stars.
So good morning, everyone. So my name is Edita Stonkute, and I'm from Vilnius University, Lithuania. And this work is done together with a PhD student of mine, Ashuta Sharma, and colleagues in Vilnius, Ernas Drazdauskas, Renata Minkevičiūtė, Šarūnas Mikolaitis, Gražina Totušinė, and the new PhD student of mine, Ugnė Janauskaitė. She's here with us. So I'm really happy to be here, close to my country. Really thanks colleagues in Tartu Observatory that initiated this project and collected we all here to talk about the stars, abundances, and the signatures of stars that can cause the planet formation. So I take the opportunity to present the observatory that we have close to Estonia. It's in Lithuania, so we are here in Tartu. And if we travel 450 kilometers, we end up here in Lithuania in Molėtai Observatory. So the Vilnius capital is here, Riga is here, Stockholm, Helsinki, Poland. So we have this nice village of observatory. Many of you have visited our observatory. It's really, as we call, is a star village, because apart from the observatory, which is here, we have Ethnocosmology Museum, really new, cool place. If you've never been to this place, come to visit us. And then we have ethnographic village, where they speak about Asian calendars and how people navigated the sky and used for daily life activities. So we have quite big building built 60 years ago, where we can host summer schools and workshops, small workshops. We can host 40 people can live there. And many of you attended summer schools there as well. And we have some summer houses over there. So we are surrounded by nature, forest, and lakes. Really cool place during the summer. If we look at the light pollution map, so here is Lithuania, again Estonia, Tartu, and this is the place with the observatory. It's quite a safe place for sky, for observations, but we have to be aware of light pollution and hazards of industry around us. So let's have a quick look at the telescopes that we use for science. So we have this Maksutov system telescope with very wide field of view for photometric observations. And we use this for all kinds of transient events at the observatory. The other one, we just recently installed the new 80 centimeter telescope, also with CCD camera used for photometry. We plan to use this for the space debris defense satellite things. And it's located in decommissioned 83 centimeter telescope. We took it away, and we installed this 80 centimeter telescope. Last but not least, one of the biggest telescope in Northern Europe, 1.65 centimeter telescope that is equipped with a high resolution spectrograph that we use for our work. So our group is quite big and quite young, and we are almost half of the whole astronomy community in Lithuania. So if you want to do astronomy, come to Vilnius, and it's only one place in Lithuania where you can do astronomy with us. So we work in Vilnius. We can operate all the telescopes remotely from our home with good internet connection. We do that with this big telescope as well. We learn our lessons. We install the spectrograph, high-resolution spectrograph. Yale University built this spectrograph for us in 2016. So it's a quite good resolution spectrograph, as you can see, 3 resolving powers, reaching up to 68,000 and having wide spectral range, very good for chemical analysis of bright stars. For this project with stars with planets, we are observing bright objects because it's only 0.1 meter, 65 centimeter telescope. And in Lithuania, we are not very lucky as in Canary Islands or in Chile. We have 25–30% of the clear nights. But when you need to observe and be alive next day, it's quite a lot of time to observe targets. So you can see the instrument itself, the spectrograph, and it's a front-end module attached to the telescope and this black box installed in the lower level room from the telescopes, isolated and nice instrument. And during this talk, I want to talk about 160 stars that we publish results of that host planets. And those planets are distributed in orbital and planetary mass distribution. We see that we have majority of our planets are coming from very massive planets. We have 32 stars in this 160 star sample that host multiple planets, at least detected so far. And it could be up to 5 confirmed planets in our sample that we have results. As Elisa presented, we use classical methods to derive the main parameters. We measure equivalent widths of the lines to derive effective temperature, log G, metallicity of a star. And we use spectral synthesis to do the abundances analysis of the elements. And in this work, we are presenting carbon, nitrogen, oxygen, magnesium, silicon, and neutral capture elements. So we use molecular lines to derive carbon, nitrogen, and oxygen. So you can see really nice examples here. So going to results, we have published, as I said, 160 stars, and those stars are distributed among dwarfs and more evolved giants, as we call. And what is good in our sample that apart from our 160 stars, we are collecting data from the same instrument from bright objects for our other projects in the observatory. And we already collected from 2016 when we installed the telescope, we already have published results for more than 1,200 stars, abundance analysis and parameters. So we have comparison data which is marked with smaller dots here. So let's go and see the results of carbon, nitrogen, and oxygen. Let's first focus on the dwarf sample because giants are a different story. I'm talking giants about the giant stars here. So in color, we see the stars that host planet, and in gray that we call a comparison sample that we think that do not have at least giant planets detected. And you can see how hard it is to derive those elements, particularly nitrogen for dwarf stars. And what we can see, basically carbon, oxygen, and CO ratio aligns with the comparison sample. We see some differences, but we need more statistics to really confirm that at a metal-rich end, we see a lower carbon-oxygen in stars with planets. But we need more data to confirm this result. And if we look at the giant stars now, let's look at this part of this figure, we see that we also aligned with comparison sample. Maybe the scatter for carbon, oxygen is lower for stars with planets. We also see this nice increase as in dwarf of CO ratio with increasing metallicity. But we don't see any differences, no significant difference between stars with confirmed planets. And as was confirmed by previous studies, we have this overabundance of magnesium and silicon. This time the stars' thick disk and thin disk is separated kinematically, but we can see this overabundance of stars and planets and a little bit underabundance of magnesium and silicon ratio in our sample. So we have many results that are published in our paper, Sharma, about stars with planets and comparison samples in our later papers by Tautvišėnė. And we looked at the cumulative distribution of comparison sample and stars with planets, and we don't see the differences when we look at CO ratio, but magnesium and silicon shows lower magnesium and silicon ratio for stars with planets. And we looked at the giants as well, because giants are affected by J effects and evolution with some abundances. And we see kind of different CDFs, but they are not significant if we run the statistical test. Last but not least, we presented results on neutron capture elements. And what we can see here that we studied neutron capture elements in 1D and LTE. We submitted a paper, but referee asked to redo the analysis implementing NLT corrections. So we did that. We reanalyzed our results implementing NLT corrections, not only for our 160 stars, but also for the comparison sample. So it took time. NLT corrections takes a lot of space and time, but we did that. Our results did not change. We still see the same trends. We aligned with galactic helical evolution, but we have some differences in zirconium, lanthanum, or cerium. We don't know what's happening with those elements here, at least at the metal poor end. We ran bootstrapping analysis to see if there is kind of mismatch because of the some things going on, but we still obtain the same differences. So we need more data, at least at metal poor end, to figure out what those signs are here. We also looked at the condensation temperature and abundance difference of stars with planets, subtracting the stars that do not host planets, and we get a lot of different slopes, as previous works are showing, that stars with planets could have different distribution of this different in the element abundances, favoring more enrichment of refractory elements. And we also looked if there is any differences in the parameters themselves from this slope distribution, from temperature, for star age, log G, star mass, metallicity, mean galactocentric distance, planetary mass, or the Zmax. There are some kind of trends, but it's really hard to tell because we are facing two different populations, like stars, massive stars, not massive, but also giant stars and dwarf stars. So there are many things to do more, and I hope my PhD student Ugne in 4 years' time will solve some of the problems that we are facing now. And my takeaway message is that we can use those facilities that we have in our countries. We just need good instruments and good people to do the observations and to derive abundance analysis that I believe is valuable for each community. And it's nice to have planetary people speaking with star people together. So thank you for your time.
Thank you. Is there a question for Edita? Yes?
Thank you for the talk. I'm just curious, did you expect any sort of differences between the two samples that you compared? And if so, what was the theoretical reasoning behind that difference?
For which element you are now referring to?
No, as in any element, but did you expect some differences between planet-containing stars and...
That's a good question for planetary people, if we can expect some differences in different elements. But this is what we see. We see that planets form, at least giant planets form around metal poor stars, for example, that are enhanced in magnesium and silicon. So as Elise was mentioning, that maybe those compensate the lack of the iron. And we see some overabundances for uncaptured elements, but this needs to be explored further because of the low number statistics, right? And bigger errors on those elements, because simply there are few lines that we do the synthetic analysis. But what we need to keep in mind that we go and check by eye each fit. It's not like we run and we trust what the black box is giving us. So it's time consuming and yeah.
Thank you.
Okay, thank you. We have to continue to the next talk, I think. So let's thank Edita again. The next speaker is Masanobu Kunitomo from Kurume University. And we'll talk about new generation solar and stellar models, including accretion.
Thank you very much. So today I'd like to introduce our solar models and stellar models, including the effect of protostellar accretion. So you know, stars are formed by the gravitational collapse of the molecular cloud cores, and at first, a tiny object is formed at the center, which is called protostar. And protostars grow by the accretion from the circumstellar disk, where planets are formed. And stars become pre-Mensheken star and Mensheken star. The key point is that the protostar is a tiny object at the beginning. The typical mass is only 0.3% of solar mass. So accretion is essentially important for the evolution of young stellar objects. And accretion injects materials, heat, and angular momentum, so it's important in these aspects. In this talk, I'd like to focus on the chemical effect, but I have also worked on the other effects. The top panel shows the evolutionary tracks on the HR diagram, and you can see that the evolution is highly sensitive to the entropy of accreting materials, which may be related to the Lara's talk yesterday. And the bottom panel shows our 3D MHD simulations. And we found that conical disk winds can lead to the spin down of protostars. So it may be the origin of the disk rocking phenomena. But in this talk, I'd like to focus on the chemical effect. And next, I'd like to introduce the composition of accreting materials. It's highly related to the planet formation processes. And planets are formed by the coagulation of dust grains. And they are initially micrometer sized, but once they become centimeter sized, which are called pebbles, they rapidly fall onto the protostar due to the frictional force with the disk gas. This figure shows a theoretical prediction of the metallicity of accreted gas as a function of time. And as I said, in the early phase, pebble drift leads to the metal-rich accretion onto the protostar. But in the late phase, dust grains deplete in the disk, or a large protoplanet can block the drifting pebbles, so metal-poor accretion is expected. So planet formation theory naturally predicts that the composition of accretion should be highly time-dependent. So the question of this talk is, does the evolving composition of accretion affect stellar composition? Of course, the answer is yes, but today I'd like to introduce our stellar evolution simulations with the MESA code, including the effect of protostellar accretion. And following the theoretical prediction, as I showed before, we modeled the metricity of accreted gas, Z accretion, like this, high Z to low Z. But for comparison, we have also simulated the case with steady Z accretion, which corresponds to the case without planet formation processes. Okay, first I'd like to focus on the sun. So this figure shows the metricity profile of the present-day sun. And the gray dashed line shows the case with steady Z accretion. Even in this case, there is a small compositional gradient. The central metricity is slightly higher than the surface metricity due to the nuclear reactions and the atomic diffusion. But in the case with variable Z accretion, we found that the central metricity is higher than by up to 5%. So this figure clearly shows that accretion can affect the compositional structure of the sun. So here I'd like to briefly explain the underlying physics. In the early phase, as I said, high Z accretion is expected due to the Pebble drift. And the stars have a free convective structure in the early phase, in the Hayashi phase. So the stellar interior becomes metal-rich homogeneously. But in the late phase, low Z accretion decreases the surface metricity. But the central region is kept metal-rich, because in this phase, in the Henier phase, the central region becomes radiative. So the high Z structure in the early phase can remain. And this structure can remain even at the present day. So the next question is, which model is correct? Of course, for the sun, we have lots of observational constraints. And we are now focusing on the central region. So, and the central region can be traced by neutrinos. So from here, I'd like to introduce our results of the neutrino fluxes. So this figure shows a boron-8 and the beryllium-7 neutrino fluxes. There are some different types of neutrinos. And the green points show the observational constraints, and the circles show the models with steady Z accretion. And you can see that these models do not reproduce the observational constraints. But the models with variable Z accretion have higher neutrino fluxes. This is because central metricity is higher, so central opacity is higher, so central temperature is higher. And of course, nuclear reaction rates are very sensitive to the temperature, so neutrino fluxes are also higher. And this particular model nicely reproduces the observation. So yeah, it's very good. So neutrino observations also suggest the variable Z accretion. And our models with accretion, and in this talk I don't have time to talk about it, but opacity increase in the solar interior is also important for helioseismic observations. So our models with accretion and opacity increase reproduce surface metricity, helioseismic sound speed profile, and neutrinos for the first time. Actually, there has been a problem, solar abundance problem, for the last 20 years. But our model could solve this problem. And also, our latest paper further updated solar models. So if you're interested, please ask me later. Okay, so next I'd like to talk about other stars with different masses. So as I said, the stellar structure evolution is very important for the chemical effect of accretion. And this figure shows that higher mass stars become radiative more rapidly. These lines show the location of the base of the surface convective zone. And you can see that higher mass stars lose their surface convective zone more rapidly due to the shorter Kelvin-Helmholtz timescale. And this figure shows the surface metricity after rosy accretion. The horizontal vertical axis is normalized by the initial metricity. So you can see that higher mass stars, the horizontal axis is effective temperature. The higher mass stars are more strongly affected by the accretion. And this is a case with variable z accretion, but in the case with steady z accretion, surface metricity should be the same as the initial metricity. So we predict that there should be a variety in the shaded region, depending on the efficiency of the planet formation processes. So to examine our theoretical prediction, we analyzed the Gaia spectroscopic data. Gaia provide stellar abundances for more than 400,000 stars. So it's a big data. And the left panel shows Fe over H and the nitrogen over hydrogen abundances. And the gray point shows cool stars. There's a trend, but it's natural with the solar abundance scale. But if we plot the hot stars, so like this, so we can see the larger scatter consistent with our theoretical prediction. Also, we found two kinds of outliers. One is a refractory poor but solar volatile star. So this may be a new lambda Boo star, and this can be naturally explained by the refractory poor protostellar accretion, as claimed by Folsom et al. 2012, Kama et al. 2015, and our paper in 2018. And also there are many stars with refractory rich but solar volatile abundances. So these stars may be explained by the planetary engulfment. And but we should be careful because such planetary engulfment signature can be erased by thermohaline mixing, or radiative levitation can also make this kind of refractory rich abundances. So we have to disentangle these two possibilities. So recently, Varda and Elisa wrote a good paper, so it's also related to these signatures. And we are now analyzing the SBAR spectroscopic data and to confirm these chemical peculiarities. And also, PLATO is very important to understand the internal structure of these stars or planetary systems around these chemically peculiar stars. Okay, that's it. Thank you very much for your attention.
Thank you. Very interesting. Any other questions? Yes. 1, 2.
Yeah, very, very cool results. So I'm starting to wonder now a little bit. The moment when you showed for the sun the plot of the metallicity as a function of radius, and the surface was 1.4, and the middle was 1.7%. And now, if you want to trace this from from a planet formation perspective, you look at all the stars in the in the galaxy to measure the metallicity, but the real metallicity is then actually higher than what we measure in the surface. So I'm starting to wonder, is there an easy relation to relate the surface composition to the overall bulk composition, what we actually care about in planet formation?
Yes. So yes, definitely the surface abundance should be different from the bulk abundances, and it's a bit hard to say, but this figure clearly shows that planet formation theory accretion can change this kind of compositional trend. So it's difficult to derive relation between the surface metricity and bulk metricity, but it's interesting. So I will look at in more detail in future. Thank you.
Okay. Okay. Any other question?
Could you say more about what was assumed for the accretion model? In particular, what was the time dependence of the m dot in the accretion model?
M dot is the Hartmann et al.'s 1997. So the m dot is decreases with time to minus 1.5.
And so then, for example, how much mass is left in the protoplanetary disk or protostellar disk at 1 megayear?
1 megayear. 1 megayear. 1 megayear. Okay. The disk mass is like 0.04 solar mass at 1 megayear.
So what if the disk was only 1% of the solar mass?
So 4%.
Well, yeah, but what if it was 4 times smaller? What effect would that have on your conclusions?
The effect should be smaller. So yeah, accretion rate or this kind of timing is the timing from high Z to low Z is very important. So we show the maximal, the best model in this talk, but of course it depends on the accretion history. Yes, of course.
Yes, I think it will be interesting to talk more about this during the coffee breaks and so on.
Thank you.
Thank you for now. Now we have Neda Hijazi from the US and Chile, and she will talk about a new method to measure detailed chemical abundances of cool dwarfs.
Hello, my name is Neda Hijazi, a very recent postdoc at University of Tartu and a former postdoc at University of Kansas. I'm now going to talk about the chemical abundance measurements of cool dwarfs and its importance in star-planet chemical connections. So because of originating from the same molecular clouds, there is a chemical correlation between a planet and its host star. So the abundances of a host star can offer valuable insight into the formation mechanism and properties of their planets. So what we need to do is to measure and compare the abundances of both planets and host stars. First, JWST is now measuring the abundances of exoplanets with remarkable precision. And second, the abundances of many hotter JWST planet hosts have already been measured from various studies. However, only a few small sample of cooler JWST host stars have reported abundance measurement. So, it is urgent to establish new and reliable methods to measure the abundances of these low mass stars in a timely manner. So this is the goal. For this purpose, the spectroscopy analysis of cool dwarf is very complicated because of the very complex spectra, which are dominated by huge number of molecular lines. And this makes the continuum identification in many spectral regions impossible. And together with substantial line crowding, some methods like equivalent analyses can be readily used for hotter dwarfs are not appropriate for cool dwarfs. And in addition, many current tools, software, and codes for stellar spectroscopy, for example, such as those using data-driven techniques, do not consider important complications in cool dwarf spectra. So we need to synthesize the spectra and model all the atomic and molecular lines and then compare them with observations. We have developed an automatic pipeline autospec fit. This is a line-by-line automatic spectral fitting code to measure the abundances of cool dwarfs. The code also performs a spectral normalization, a line-by-line spectral normalization, which is based on carefully selected data point in pseudo-continuum around each selected line, which is critical, very critical for a proper comparison between observed and model spectra. The method also considered the correlation between the abundances of different elements in an iterative manner. The code requires Mark's model atmosphere, atomic and as a custom set of atomic and molecular line lists, and also a spectral synthesis code Turbo Spectral. Using a high-performance computing system with job scheduler, the code itself takes around or less than 2 days for each single star. But if the required input data has already been provided, that I will talk about this later. So we have applied our method to several stars. For our pilot study, we measured the abundances of WASP 107, which is a late type K dwarf and has a super Neptune, super puffy Jupiter-sized planet. The planet has been targeted by several JWST programs, which have so far detected some key species such as sulfur dioxide, carbon dioxide, and water, or measure abundance ratios involving elements, planet building elements such as carbon to oxygen ratio and magnesium to silicon ratio fall into the ranges of the stars in the solar neighborhood. HST analysis has shown that the planet seems to have a low carbon to oxygen ratio, the planetary values, but because the planet is inside the water ice line, a lower planetary carbon to oxygen ratio relative to stellar value is expected. But ongoing JWST studies on this planet will for sure measure the abundances at abundance ratio of the planet more accurately. We have next applied our technique to planet host M dwarf K218, which the planet has also targeted by multiple JWST observation. And the early JWST analysis has shown an unusual, an atmosphere with an unusual chemistry, dominated by kind of methane and carbon dioxide, which is unlikely to be driven by the formation of the planet in a disk with unusual composition. And again, ongoing JWST observation about this planet will help us better understand the properties of this planet. Our recent studies is about the chemical links between a young M-type T-Tauri star, DH Tau A, and its very widely separated super gas giant companion. The star has a considerable magnetic field and mild projected rotational velocity, which were taken into account in our analysis. or measurement of carbon to oxygen ratio for the star is fully consistent with that value of the companion, which suggests a formation mechanism for the companion compatible with direct and fast gravitational collapse rather than a slow core accretion process. This suggestion also supported by the system age. The DH tau system is extremely young, making a core accretion formation scenario also again unlikely. Our method has shown to be also successful in optical spectra. We measure the abundances of 5 elements for metal pool M sub-dwarf LHS 174. The optical spectra of M dwarf and M sub-dwarf are dominated by millions of titanium oxide molecular line, which are not, many of them are not even consistent with models, even using the most recent line list. Similar to H2O lines in NIR region, which is sometimes so frustrating. But we have found a small portion of a specific titanium band, which is well modeled and can be used to measure oxygen abundance. The chemical abundances of metal poor star can give us important information in the chemical enrichment history of the Milky Way, but M sub-dwarf in particular are faint and are, on average, are located farther away from the sun compared to the disk stars. So only a handful of these stars have a spectra with sufficient signal-to-noise ratio for abundance measurement of additional elements. So it demands observation of many more of metal poor M sub-dwarf with large telescopes and with long exposure times. For our ongoing work, we have measured the we have applied the technique to M dwarf hosting a rocky sub-Earth planet. The early JWST studies have shown a consistency with model having no atmosphere, making the planet an ideal object for applying interior structure model with minimum degeneracy. But the problem is that for this specific planet, there is no measured mass. But we using exoplanets, a mass radius composition solvent, and an MCMC sampler, we were able to roughly estimate the mass of the planet as well as some chemical properties of the planet. But for this project, we will add 8 more stars hosting rocky planet, but with measured mass, which will provide for sure additional constraint to derive the properties of planets much more accurately. So I'll just stop here and go back to the method. In addition to many factors, abundance measurement of cool dwarfs is highly sensitive to spectral normalization. Stellar spectra are often normalized by performing a FET over a rather broad spectral range, and usually without using any synthetic spectrum as a reference. So there is a problem with this approach. First, because the continuum, it cannot be identified. What is modeled by the fitting may not show the continuum, or even may not show the pseudo-continuum because of spectral noise, bad pixels, or other anomalies in observed spectra. Second, Spectral feature and slopes of cool dwarfs change rapidly from one region to another, and fitting over a broad range may not correctly present the variation in the all wavelength interval inside the range. And the third, the results are the results strongly depend on the type of the fitting. And on the other hand, the normalization of the observed flux using only one single synthetic spectrum as a reference may not be also sufficient, because the pseudo-continuum is affected by the abundance changes. So auto-spec fit actually overcome all this problem by locally normalizing the observed flux for each selected line over short wavelengths with respect to each generated continuum normalized synthetic spectrum used in chi-square minimization. So far I have presented very good things about auto-spec fit, but it has a problem. The preparation of the required input table needs a very careful visual inspection and is very time consuming. So the process should be automated. I have been recently developing a code an automatic code which automatically normalizing which are normalizing the observed spectral automatically searching for data points in pseudo-continuum around each selected line. But the code is now being tested and modified, and but it has been actually it is very complicated code and include many various steps, but it has been very promising. And so, thank you so much. And this is.
Thank you. Is there one question? We don't have much time, but one question. Yes.
Thanks, Neda, for the talk. So I wanted to ask you what is the most difficult element to derive in the near infrared, and what was the lowest temperature you could reach for the normal dwarfs, not for the subdwarfs?
So the most difficult elements, I think, would be some potassium. For myself, is a potassium, and because maybe it's kind of affected by a non-LTE, because my method is LTE, and the lowest temperature that I can go with this method is 3,000. It's not less than that. Yeah.
Mm-hmm. Okay, thank you. Also, this we can discuss more in the coffee breaks, I think. Thank you again. And we continue with Jia Yue Chang from Beijing, talking about chemical abundance patterns of solar analogs hosting debris disks.
Yeah, so good morning, everyone. So first, I want to thank for the organization to offer me a chance to give a talk. And I am Jia Yue Zhang, a PhD student from Tsinghua University, China, and working with Sharon Xuesong Wang. So today, my talk is about our preliminary results of the chemical abundance pattern of solar analogs with debris disks. Okay, so here is my outline. So first is a background and motivation. So I want to introduce our solar abundance anomaly first, and then introduce some existing theoretical hypotheses, and briefly introduce our project PASTA, and then explain why we choose debris disks. So here, let's start with a solar abundance anomaly. So here we can see this plot. The axis is the condensation temperature of each element, which means that how easily the element can condense into the solid. And the y-axis is the elemental abundance difference between the sun and the other elemental abundance of our nearby solar twins. So the values above 0 means that the sun has more elements compared to the solar twins, and the values below 0 means that the sun is depleted compared to, of that element. So we can see that as the condensation temperature goes higher, the sun seems like it's depleted in the refractory elements, which is the condensation temperature is higher. Yes, this is the solar abundance anomaly. So there are several existing theoretical hypotheses to try to explain this anomaly. So first, Chambers, they suggest that when the planets form, they lock up a large amount of the refractory elements in their solid bodies. And Booth and Owen propose that the giant planets like Jupiter can create dust traps during in the protoplanetary disk, and these traps can prevent the inflow of refractory rich solid dust go back onto the star. And another hypothesis is that the engulfment events where a star can consume the rocky bodies, rocky planets, this could increase the abundance of refractory elements. So to address this hypothesis, we first start with a PASTA project. So here I want to briefly introduce our PASTA project. It is focused on understanding how planet formation affects the stellar chemical compositions. So by studying the solar analogs hosting planets, we aim to reveal whether the presence and the type of the planets correlate with the depletion or the enrichment of the refractory elements. So this is led by our collaborator Qinghui Sun and Dr. Qinghui Sun in Shanghai. And in my part, I lead a disk extension of PASTA called D-PASTA. So we explore solar analogs with debris disks to investigate whether the leftover planet building materials can leave measurable chemical fingerprints in the solar stars. Therefore comes our questions: why the observations of debris disks can help, or to say, why we choose debris disks. So from the first perspective, the perspective of theoretical explanation, as debris disks are the remnants of the planet formation processes, they can provide insights into how material distribution around stars may affect their surface abundances. So the first point is that the existence of a disk means that there is still a lot of solid material around the star, and that solid material is likely to locked it into the planets and didn't fall into the star. And the second point is that the debris disks usually trace dynamically hot situation. So recent collisions or scattering events may even throw some materials into the star. So if we can observe one correlation between the presence of debris disks and some specific abundance patterns in stars, it could imply that one of the mechanisms have contributed to the solar abundance anomaly. However, if no correlation is observed, this can also provide some valuable observational constraints on this interesting population. So the second point is that there is in general a lack of studies linking stellar abundance and debris disks. So first, solar analogs are great samples for studying the stellar abundances due to their similarity to the sun. And on the other hand, there have been very limited studies on the disks around the solar analogs. And Gaia data offers a large catalog of solar analogs with accurate spectroscopy measurements. So this can provide new opportunities to study these stars with high precision. And this combines with a detailed debris disk catalog can offer us new insights into the population of disk hosting solar analogs. And so with this context, the primary question we aim to address is there any difference between solar analogs with and without debris disks in the elemental abundances? So before diving into our preliminary results, let's start with a quick question. So we have a huge catalog, nearly like 20,000 of solar analogs. And from those, about 5,000 high-quality golden samples with precise parameters. So now we cross-match them with our all-known debris disk catalog. So how many debris disks, so how many solar analogs do you think with debris disks? 10? A bit more? Yes, the answer is only 69. So out of like 20,000 solar analogs, only 69 have confirmed debris disks. And among these, only 8 are we call solar twins. So this plot is our samples. The x-axis is metallicity, y-axis is surface gravity, and the color bar is the effective temperature. And the red stars are the solar twins, which means they have more tightly stellar parameters compared to our sun. And the green one is 9 of them already have the elemental abundances available in the literature, and our preliminary results today are based on these 9 samples. So, and to investigate the abundance differences between the solar analogs, so I adopt a two-step approach. So first part is the framework to derive the stellar abundances using SED fitting and isochrone fitting to get some stellar abundances, stellar parameters, and then use these parameters as input, and with a high resolution spectrum, we can do the abundance analysis. And my pipeline, I use the equivalent width method using the iSpec and Moog. So we finished the initial iterations, but the results are not final yet, so I will show some preliminary findings next. So first, this is a quick look at the abundance pattern of disk hosting solar analogs using the existing measurements from the literature. So in this figure, each blue and red point represents the difference of the elemental abundance between sun and the other solar analogs. And the orange solid line is a linear fit of this average of the elemental abundance difference. So it is consistent with what we found in the PASTA project, and also close to the trend seen by Melancy for the solar twins. However, this overall slope seems to be mainly driven by volatile elements. So if we fit only the refractory elements, which is a green dashed line, it looks like the slope becomes much flatter. Maybe it can indicate that there is a weaker refractory depletion is seen in these disk hosting solar analogs. So, which means it's more similar to our sun, but we caution that it's a very small sample, only 9 objects, so it's not conclusive yet. Yeah, and another thing, here I place a previous figure with PASTA project. The upper panel is our samples of 11 planet hosting solar analogs. And the lower panel is the same, but from another literature. So we realized recently it's the problem of the repeatability and the precision of these measurements from different instruments or even different groups. So now we want a homogeneous and a robust data set. Okay, so here is our future work, and let me just get a summary part. So although our results are still preliminary, I hope they can spark your interest in this interesting question, and I'd love to discuss with people who are interested in this problem and the weaker refractory depletion we saw in our preliminary work. Yes, and thanks for your attention.
Thank you very much. We have time for 1 or 2 questions. Both were at the same time. Let's start with Vardan.
Thanks for the talk. Very, very interesting project. And I was very happy to see that you are also deriving ages of the stars, right? So blind formation engulfment can, in principle, change the composition of the star, so you can have this slope or whatever, but the abundances mostly should be driven by the galactic chemical evolution. So I was wondering whether these slopes that you see changes with age of the stars. Have you checked that?
Yes. In the PASTA program, we did the GC correction, and the TC slope won't change much. It's just like this.
Okay. Thank you.
Okay. Yes, please.
When you define your sample of solar twins and solar analogs, do you account for the fact that the sun was cooler and had a higher surface gravity when it was at the age that's typical for debris disk hosting stars?
You mean the age effect?
Well, so the sun is getting hotter with time,
yes,
and its surface gravity is going down. It's getting puffier. So do you account for that when you select your solar twins and solar analogs among the younger stars?
Yeah, that's the question we are interested in. So we did the isochrone fitting to get the ages of our samples, and the sun looks like it's like in the middle of our samples, but I didn't make a plot. So yeah, actually the first motivation of this project is I want to see where is our sun in these samples. So we will figure out it.
Okay, then let's end this session. Thank you again, and thanks to all the speakers again. And we are we took a bit longer, 5 minutes about or so. So we start 5 minutes later the next session, so 11:35. Okay, welcome back to the second part of the session on stellar chemical composition. And the first talk after the coffee break is by Sandipan Portakur from Austria, I think. Yeah. And he will talk about stellar photospheric contamination in early type stars.
Close enough here. Hi everyone. I'm partly in Austria and partly in Estonia. So, okay. So I will talk about stellar contamination from protoplanetary disks in early type stars. So early type would mean hot stars above, let's say, around 6500 Kelvin. So before I go into my results, I just want to give you an introduction of what I do. So as you see, this is a protoplanetary disk. Everyone is familiar with it. And at the center is your star. And what I'm looking at is the accretion of these materials, which contains both dust and gas, and which is accreted onto the star. And I'm looking at this white circle around, which is the stellar photosphere. So one of the things that's affecting the accreting material onto the stellar photosphere is formation of, for example, giant planets, which prevents the pebbles or dust, heavier dust, to move inwards and accrete onto the star. So you have accretion of dust-poor material on the stellar photosphere. Now, if you look at hotter stars, so around stars with temperatures greater than 6500 Kelvin, you have stars which have a convective core, but a radiative envelope. But if you look at a star like our sun, you have mostly a convective envelope, and then any accretion onto the star gets mixed quite evenly, although some of the people have shown that you still might see something here. So I'm looking at these early type stars with very slow mixing and a long-term accretion composition impact on the photosphere of the star. So just to give you an example of the same idea, this is, for example, the water which is getting accreted onto the photosphere, and the red dots represent oxygen, H2O, yes, oxygen and 2 hydrogens. So these are the red dots which are getting accreted on the photosphere. And even after the disk is dispersed and you don't have a protoplanetary disk, you still get an oxygen which is accreted from the disk. So just some definition which varies between what you ask people. So I define all the elements which are mostly found in dust as refractory elements, and all the elements which you mostly find in gas as volatile elements. Okay, so this was one of the results that was shown in Kama et al. 2015, which is that if you look at stars with gaps in their disk due to formation of giant planets, they show a lower abundance on an average of iron, magnesium, or silicon compared to stars with no gaps in their disk. But on the other hand, if you look at the carbon or oxygen abundances in these two stars, which are represented by black diamond and the white diamond, you see that carbon and oxygen are more or less the same in both types of stars with these different disks. Which is interesting because then you can compare, assuming that all of your iron in the disk is in dust, you can compare how the iron abundance is compared to other elements. So for example, if you, so these are volatiles and these are refractories. So for example, if you do that for oxygen, you see that compared to iron, as the iron abundance changed due to different amount of dust accreting onto the star, the oxygen does not change because the gas accretion was not affected by giant planet formation, for example. But if you look at titanium, I know the uncertainties are quite big in some, but on an average, you see that it follows this correlation line. So if you have a flat line like this, it means that most of the oxygen is in gas phase. So the slope is 0. If you look at titanium, then the slope is almost 1, then most of the titanium is locked in dust in the inner disk. So one of the questions that we had was, what about phosphorus? As most of you probably know, that phosphorus is quite difficult to observe, and I don't think it has been observed in a protoplanetary disk. But we can do this same test for phosphorus and see what we get. And we measured phosphorus abundance in these early type stars with protoplanetary disks. We used Hubble archival spectrum, a high resolution archival spectrum from STIS. And what we observe is that, again, if you have stars with no visible gaps in the disk, you see on an average the phosphorus is here. And if you have a gap in the disk, it's depleted, which means that the phosphorus is locked in dust. But we can also quantify how much of phosphorus is locked in dust by, again, doing the comparison between phosphorus and iron. And that's what we did recently. These are all the Herbig stars, so A-type stars with protoplanetary disks, with HST spectrum available in high resolution. And when we fit this data, we get a slope of 86%, which means that around 86% of phosphorus is locked in dust in inner protoplanetary disk. Maybe you see that when I'm talking about slope, the line should not be a curve, but that's because both of the axes are in log scale, and we are fitting the straight line on in absolute scales. And so that's one of the results that we see for phosphorus, and it would be interesting to understand how the phosphorus is locked in protoplanetary disk and in what reservoirs it's locked in. Another interesting aspect is oxygen. As you have heard probably in the last few talks, oxygen is interesting. One of the observations that we had recently was that when we looked at oxygen abundance in Herbig stars and in young debris disk hosting stars, all A-type stars, then you see that the oxygen abundance do deplete over time. So you can ignore what blue and red are, just assume both of them are Herbig stars, and the black ones represent young debris disk stars. And you see that at young ages, around 10 to 20, below around 20 million years, you see that the oxygen abundance is depleting over time, but the carbon abundance stays more or less the same. I haven't plotted the age uncertainties because I'm not quite sure how different references define the age uncertainties quite differently, and I was not sure. So the position of these stars might change a bit, but on an average, they still show this oxygen depletion. This is just a zoomed in version where I cheated. I removed even the other uncertainty, just to see that we do see an oxygen depletion in Herbig star photospheres. That's something people have seen before, at least theoretically, in Ma et al. 2024. And I want you to focus on this figure. And they have modeled how the inner disk oxygen abundance changes over time, depending on the formation of gaps and their gap strengths. So at different gap strengths, you see that the oxygen abundance do deplete over time in the inner disk, and which might explain why we see an oxygen depletion in Herbig stars. But we need to test this, and all the data is just observational right now. And I'm drawing the same plot, but extended the sample a bit. So the blue data points here represent, again, Herbig star oxygen abundance. And you see that the oxygen abundance is depleting over time. But when you look at older stars, main sequence stars with a debris disk, with a giant planet, or with no disk observed at all, you see a large diversity of oxygen abundance, which has also been reported in earlier publications. And what might explain this diversity in oxygen abundance is that these stars have evolved out of their protoplanetary disk hosting sequence at different points during this depletion. And so if they evolved out from here, they would have an oxygen abundance somewhere here. If they evolved out around here, then they will have an oxygen abundance somewhere up. although it's more complicated than that because you also need to consider mixing in the stars and how that affects the oxygen abundance. But that's something we want to test later. Okay, so I'm almost done. So my conclusions are simple. So we saw that phosphorus is mostly locked in dust in inner disk, but my question is, can we identify what reservoirs the phosphorus is locked in from this? And we also saw that the oxygen abundance is depleting in Herbig stars, but what's the origin of this is still not clear, and something we would like to test is to combine a disk evolution and a stellar evolution model, similar to what I think Masanobu has done. So yeah, thanks.
So, there is time for questions. Yes?
Yeah, very cool results. I was wondering, in the very beginning you showed that the oxygen abundance would stay the same no matter if you have a gap in the disk or if you don't have a gap in the disk. And I was wondering why that is, because a fraction of the oxygen should be locked in the refractories that should also be blocked by the gap. So I would naively expect that there should be some differences for oxygen as well.
Yeah, that was one of the problems we have. I think that some of this, we see a scatter in the oxygen abundance, so some get lower. So I think the oxygen depletes over time, but in the beginning, they more or less stay the same. Yeah, because it's also dependent on the stellar evolution, because they have a convective envelope at the very beginning. So even the depletion in the disk might not affect the star in the early stages. So probably that can explain it. But yeah, I think we need to model the disk plus star together.
Okay, I don't see any more questions. Then thank you again.
Yeah, thanks.
And we continue with Veronika Mitrochina from Tartu, who will talk about the detectability of deuterium in the spectra of A-type stars.
Hi everyone, my name is Veronika. I'm PhD student here at Tartu Observatory, and today I would like to talk about detectability of deuterium in stellar spectra. So what is special about this topic? As was already told before, that primordial nucleosynthesis is the main source of deuterium. Deuterium level was estimated like 2.5 by 10 to the power minus 5. But in stellar spectra, we usually don't expect any deuterium because deuterium is very fragile and it is easily destroyed in stellar interior by fusion. So that's the reason why we don't expect any deuterium by default. And if we can find any deuterium line in stellar spectra, it might be result of chemical pollution. So, for example, engulfment of deuterium-enriched gas giant or certain amount of ice bodies that could temporarily enrich deuterium level on stellar surface. However, we are not expecting this signature being long-lived because of convective mixing, although under some circumstances, under some condition, we can detect deuterium longer. So, for example, if we have a radiative envelope, then we can find deuterium and detect it. So, on this slide, for your reference, you can see deuterium level in some of our solar system objects. You can see deuterium level on Earth, some planets, and also ice chemistry in disk and comets. You can see that they're highly deuterite. Maybe you have heard about comet Churyumov-Gerasimenko, that deuterium was also measured there. And you can see that under certain mass, deuterium start to be fused. So okay, we can theoretically find deuterium, but then the question is, can we actually resolve deuterium line in the presence of much more prominent hydrogen line? And to answer this question, we did some modeling using Zeeman radiative transfer code. And as you can see here, this is optical region, and on the right plot, you can see H alpha optical region, and on left plot you can see H beta, and with the same deuterium abundance, deuterium line is a bit different. So here you can see that H alpha much more sensitive to deuterium, and if you're about to look for deuterium in optical, it will be obvious place to have a look. Okay, so unfortunately, it's not that simple as in model spectra. Usually we have some noise, and the question is how much deuterium should be in the spectra so we can detect it. So here you can see example of really good high-resolution spectra, so signal-to-noise ratio around 1,000. It's not that bad. All deuterium lines that were modeled are clearly resolved. Although in reality, in majority of the time, we have a situation like this, that is signal-to-noise ratio around 100. Okay, and you can see that already some of the line with some abundances are not visible anymore. So to estimate upper limit, how much deuterium you actually have to be able constrain it, we use some tools. The one that I already mentioned, that is Zeeman code on left scheme. So basically, it is our radiative transfer code, our spectra synthesis code. We use as an input model atmosphere, Atlas 9, a list of atomic data, Wald list, and we manually insert deuterium lines from NIST database. Also, we have used set of chemical abundances and partition functions that were recalculated for deuterium. After that, Zeeman integrates radiative transfer equations, produce synthetic spectra, and after chi-square fit and routine, we got stellar parameters and uncertainties. So this is the core in our MCMC analysis. Let's move to right plot. Let's start from bias theorem. In our case, we are mostly interested in nominator. That is basically our MCMC analysis. So in nominator, we have likelihood and priors. So basically, we are interested in Bayesian inference of stellar parameters by sampling posterior distribution. And to have it done, we used Python packages, that is MC and Corner. Okay, so after analysis, we got some posterior probability distribution. As you can see here, this is example of weak detection for stars with different temperature. We used temperature range that is more or less related to A-type stars, that is like 7,500, 10,000, and 12,500. Signal-to-noise ratio is 200 for all synthetic spectra here. Yes, and for reference, we put abundance 4.5, applied some noise to our model spectra, and retrieve example of weak abundances of probability distribution. So here you can see that for cooler star, our Gaussian is a bit narrower. It means that analysis is more robust for cooler star. And this is example of upper limit. That is actually the thing we are interested in. So we see probability distribution and some threshold in here. So you can see that upper limit is a little bit different for different temperatures. that is temperature dependent. And basically it means that we can have who wants less deuterium but no more than this threshold. So yes, this is example of non-detection. And then we build upper limit as a function of signal to noise ratio and different temperatures. So again, this illustrates that deuterium upper limit is temperature dependent, that for 7,500 Kelvin star deuterium line is much better constrained. And yes, and for this graph, we used 99 up to 99.9 confidence interval. And after that, we decided to check our methodology on real stars. So the most obvious choice was to look at cooler end first. So this is example of 7,000 Kelvin star, HD 3211.5. We took stellar parameters for the feed, for like initial feed from Lucas Fossati paper, and then we feed our synthetic model to real observation. So you can see that this is observational data of espadons. Signal to noise ratio is 200 here. You can see where the deuterium line is supposed to be, and it's pretty clear there is no line here. And that is the most important, in green frame, we see already a familiar plot that we have seen before. That is example of our upper limit. So with this star, we are running to upper limit. And we also checked it out for 21 pegs, that is chemically normal 10,000 Kelvin star. And you can see that actually we run to upper limit as well. But numerically it is a little bit different, but still we don't have certain Gaussian, we don't have certain peak in there. For 21 peg, we have spectra with signal to noise ratio around 1,000, and we estimated deuterium line out of H beta region. Yes. So to conclude, I would say if you prefer to look in deuterium line in optical, H alpha region will be the obvious choice. MCMC analysis reveals several clear trends. So for example, the one that is signal to noise ratio with increasing, we got upper limit of deuterium decrease. That is pretty logical. The more clear spectra you have, the deeper you can see. And also, deuterium upper limit is temperature dependent. So it's better to look for it in cooler end, 7,500 Kelvin star. And yes, and we applied this methodology for several real stars. And yes, it confirmed our method. And we are still about to test it out on other stars as well. Okay, thank you for your attention.
Thank you. Questions? Yes, please.
Very interesting. Could you show the deuterium abundance of the hot stars? Yellow, green.
This one.
Lines? Before.
Before it is for cool star.
Sorry, there's a histogram of the probability.
Uh-huh.
So hot stars have, just before that, sorry.
Yeah.
Okay, so hot stars have a higher deuterium abundances, right?
No. That is the thing that we have deuterium abundances the same for all three stars. We applied noise on this synthetic spectra and then estimated upper limit out of it.
Okay.
Yes.
Okay. And I remember that Jeff Linsky in Colorado analyzed fuse data, so the Lima alpha line. So can you use it for comparison?
Yes, for Lyman alpha line. We also model it, but we haven't checked it out yet, so it will be the scope for future work. But as you can see in synthetic data, we also modeled the deuterium line, and it's much more prominent, but there are extra complexity in this region, so that's why we stopped on optical so far.
Okay, I can ask a question then too. So the hydrogen line regions, I would say can be difficult to in the observations with the continuum normalization. How do you deal with that in the observations?
Mm-hmm. So, as I mentioned, right now we work with optical wavelength region. So basically, I normalized spectra myself near hydrogen line, and right now we are fitting only a part of the hydrogen line. So it's not the full line including core. It's just a wavelength region with deuterium line inside. So that's basically the reason why we are not reconstraining temperature and log G on this corner plot properly, because it's just a part of the hydrogen line, not fully.
Okay, thank you. Then thanks again, and we continue with Karolina Szewczyk from the University of Leeds, who will talk about a disk caught at the transition from protoplanetary to debris stage.
Okay, so hi, welcome everyone. My name is Karolina Szewczyk, and I'm a PhD student at the University of Leeds. There I work with Dr. Olja Panic, and today I'll talk to you about HD44892. This disk we caught at the transition from protoplanetary to the debris stage. So I first thought it would be good to explain to you what debris disks are and why we study them. So debris disks are these belts of planetesimals and dust that orbit around their host star, and they can be thought of as analogs to the solar system's Kuiper or asteroid belts. Compared to the earlier evolutionary stage of protoplanetary disks, they do not contain much material in them, and that is mainly dust. So protoplanetary disks are the earlier evolutionary stage, and in contrast to debris disks, they are these continuous structures spanning from the star out to the outer regions of the system, and they do contain a lot of material in them. That is mainly gas with some dust in it, with the ratio being 99% of gas to 1% of dust. So once the protoplanetary disk disperses, only larger bodies that have formed, such as planetesimals and planets, will remain in the system. And these bodies will then continue to collide, grinding down into smaller and smaller bodies, eventually creating dust. And this secondary origin dust is what we detect in debris disks. So just like the primordial dust in protoplanetary disks, the dust in debris disks will also produce infrared radiation on top of what we would expect coming from the star itself, which we can detect as excess. But because there is much less dust inside the debris disk compared to protoplanetary disk, the level of excess will also be much lower. So here you can see some examples of protoplanetary disks and debris disks at much, much lower fluxes. That means we can set an observational division between what is a protoplanetary and debris disk based on the level on that excess, and we follow such division that was introduced by Iglesias 2023, where at the level of 12 micron, debris disk will have this excess below 2, and protoplanetary disk will have it above 25. But what about this region between 2 and 25? Well, that's where we expect another class of disks to reside, called hybrid disks. So these are hybrid between protoplanetary and debris disks, so they will have some characteristics of both. And we expect them to have already secondary dust, but the gas in them will, at least in some stage, be still of primordial origin. So let's talk about this gas a bit more now. Historically, debris disks used to be considered entirely gas-free until the discovery of gas in the debris disk of Beta Pig in 1985, which to this day is one of the best studied examples of a debris disk with gas. Since then, we have detected gas in almost 50 debris disks. That is mainly around A-type stars, as you can see here. And there's two main scenarios as to where this gas may come from, primordial and secondary. So secondary gas is produced alongside dust inside the debris disks through, for example, collisions or sublimation of planetesimals, whereas primordial gas will be left over from the protoplanetary stage. And it also implies that the dissipation of gas at the end of protoplanetary disk lifetime is not as efficient as we once thought. We currently don't really have an easy way to distinguish between what is primordial and what is secondary gas, but we think it is the youngest disks with the most CO gas mass in them that will still have primordial gas, just like HD 141569, which is the only known to date pre-main sequence intermediate mass star to host a debris disk with gas. But why does any of this matter to you? Well, it was shown that secondary origin gas in the debris disk can have a massive impact on the atmospheres of planets. So it can actually enrich or even fully replace the primordial atmospheres of terrestrial planets, completely changing their impact for habitability. So the target we have looked at is HD 44892. It is also a pre-main sequence intermediate mass star. So it's located just under 200 parsecs away. It has an age of 2 million years, a mass of 2.9 solar masses, 60 solar luminosities, and a temperature of 7,500 Kelvin. So if you remember what I said before about being able to observationally set this division between what is a protoplanetary and a debris disk, here you can see exactly how it works. So HD 44892 at the wavelength of 12 micron has this fractional axis of 7.86, which puts it exactly between protoplanetary and debris disks, just like HD 141569. So we searched for gas in this object in two ways, with gas emission and gas absorption. So I'll first discuss our ALMA results, where we have looked for emission of continuum, 12CO, 13CO, and C18O, with all the lines being J221 transitions. And we have detected 12CO emission and dust emission at 6 and 9 times the noise level, respectively. So our gas emission, which you can see up here, is not spatially resolved, but we do resolve it kinematically. So you can see the red and blue shifted parts of the disk, which indicate that the gas is rotating in the circumstellar disk around the star. Our continuum emission, on the other hand, is marginally resolved in the major axes. So with the ALMA fluxes, we're able to estimate the dust and CO gas masses in this disk, and we find that the dust mass is of the order of 10 to the minus 2, and the CO gas mass from the 12 CO line we have detected is 10 to the minus 4 Earth masses. We also used our upper limits from the non-detections of 13CO and C18O to estimate what the CO gas mass in the disk might be up to, because we don't really know if the 12CO line we have detected is optically thick or not. And we find that this gas mass could be up to 10 to the minus 2 Earth masses. On the plot here, we are comparing the CO and dust emission. So the 12CO is here in black, and the dust emission is in this like orangish color. And like I said, 12CO is spatially unresolved, so we can't really say much about its morphology or distribution, but our dust emission is indeed marginally resolved in the major axes. And you can see that it is elongated in the major axes. It extends a bit more to the northwest, I think, of the star, which might be pointing at some hidden asymmetries in the dust disk. So using ALMA, we were also able to compare to other known debris disks where CO has been detected. So there is two plots here. The first one is the dust mass versus age, and the second one is the CO gas mass versus age. And we have HD 44892 here, and the two limits from the 12CO and 13CO non-detections. Debris disks are in general marked with circles. Some of the more better known ones have like colors. And protoplanetary disks we compare to are here and here in squares. So we've also marked HD 141569 right here and right here, which is the only other known pre-main sequence intermediate mass star to have a gas-bearing debris disk. And comparing the two objects directly, you can see that the dust mass may be of quite a comparable amount, but the gas mass is where the two really differ. It is possible that the 12CO we detected is indeed optically thick, and that bridges the gap between the two objects slightly, but we can't really tell with the current data. So at the moment, we think HD 44892 has both its dust mass and the CO gas mass at a level comparable to your most average debris disks. So secondly, we looked at it with UVES to search for gas absorption. And we have 2 observational epochs. So each column here is a different observational epoch. Each row is a different line we have looked into. So that's ionized calcium K and H lines and sodium D1 and D2 lines. The residual spectrum of our target HD44892 is plotted in black. All the different colors are the residual spectra of nearby stars we compared our object to. And the different regions marked here are the radial velocities of known interstellar clouds in the line of sight to our object. So we have found that HD44892 has this very, very prominent interstellar feature, which is caused by a cloud of gas in the line of sight to our object. And you can find it in the spectra of nearby stars. And you can also see that it correlates to the radial velocities of the clouds that we know they are there. But aside from this, we found this really interesting variable feature that is present in both of the calcium lines, and it changes between the 2 epochs we have looked into, but it's completely absent from the sodium lines, and we don't see it in the spectra of nearby stars. So we do think that this variable feature is due to transient circumstellar gas. We also checked the H-alpha line, and you also have the 2 different epochs, and we find that the spectrum of the H-alpha is made up of emission and then absorption features, and that in the second epoch, the absorption seems to be stronger than the emission, and it actually extends below the continuum line. So we also find similar variability in the H-alpha. From H-alpha, we were able to find that the gas is being actively accreted at a rate comparable to your standard Herbig stars. But more importantly, because there is that correlation in the variability between H-alpha and what we find in calcium, we think that both of these have variability due to being actively accreted. So the calcium gas we find in the disk has to be very hot, has to be located close to the star. And because it is actively accreted, we do think that this gas is still of primordial origin. So just to conclude, we report a new detection of 12 CO and thus continuum emission coming from the debris disk of HD44892. And this disk is now the second known pre-main sequence intermediate mass star to have a gas-bearing debris disk alongside HD141569. The CO gas mass and the dust mass we find from the ALMA results make it comparable to other known debris disks with gas, but it is possible that the 12 CO line we have detected is optically thick, and that would increase the gas mass slightly more, possibly making this disk CO rich. We've also looked at this object with UVES and found variable transiting gas in ionized calcium lines. We've also found similar variability in the H-alpha line, suggesting ongoing gas accretion, and we think that this gas is still of primordial origin. That is all from me. Thank you very much, and I'll take any questions.
Thank you. Questions?
Very nice talk. Maybe I missed it. You said it, but do you have a sense of how quick is it? Can this phase be compared to maybe the protoplanetary disk based on your population diagram at some point that you showed?
How quick what?
How quick or how slow is this phase, or this debris disk phase? Do you have a sense of that?
How quickly it disperses, or?
Yeah, I mean, from the protoplanetary disk phase to the debris disk phase, do you have any clue whether it is like omega E or less than that based on your...
Yeah, so compared to your standard debris disk, it must have lost this protoplanetary disk really, really quickly. So this here is no loopy, which is also a really, really young debris disk. So it's also lost its protoplanetary disk really, really fast, but probably for different reasons, because this one is a low mass star, whereas ours is almost 3 solar masses. So we are continuing to find these really, really young debris disks, but we don't really know what causes them to lose the protoplanetary disk much quicker than what we would expect, because your standard division would be 10 million years, right? And then from that, you would have a debris disk before that would be a protoplanetary disk. But you can really see that the level of dust mass we have here compared to, and these are the lowest in mass protoplanetary disks, is really, really low, and it really firmly places it in the debris disk category.
Okay, thank you.
Yes, another question.
Sorry if I missed that. Do you have Or do you predict photometric variability of these stars due to this transient gas, and do you have observations, photometric observations in the optical gas?
I'm honestly not sure if we have looked into it, because that's not really something that was part of my work. But we for sure know, as much as we can, that it's not a binary, so that the changes in the spectra are not caused by binarity, but I haven't looked into the star itself now.
Thanks.
Okay, one more question here.
So do you have a X-ray or UV luminosity constraint on this object?
No, we are currently trying to get more observations and proposing for each instrument we can, but not at the moment. This is all we have. It's just ALMA and the past UVS data, and that's it.
Okay.
Yeah.
Okay, thank you.
Okay, there are no more questions. Then thanks again.
Thank you.
We continue with Andrea Perdomo Garcia from the Max Planck Institute for Astronomy, who will talk about planet hosts again. Now back to planets, and tell us that most planet hosts have subsolar metallicities, but solar or supersolar iron.
Okay. Hello, everybody. So I'm going to talk about the work I've been doing this year with Maria Bergeman and Bertram Beach. And, well, this sometimes happens with ongoing work. We thought we had this result back when we presented the abstract to the conferences, but actually this doesn't stand anymore. So let's retitle the talk and talk about planet formation viewed from the mass fraction of the stellar hosts, from the metals mass fraction of the stellar hosts. So the motivation is pretty well known in the audience, but I'm going to highlight it very quickly anyway. So if we want to know how the planetary systems are formed, we need to know the environment in which the planets are formed. So for that, we are interested in the composition of the protoplanetary disks. But of course, in the already formed systems, we don't have this information. So we typically use, for example, the metallicity of the star itself, which is contained in the metal mass fraction. So we use this metal mass fraction of the stellar hosts as a proxy of the composition of the disk where the planets form. There are many results based on the iron abundance. Lately, more results based in other elemental abundances studies. For example, when we saw that the occurrence of gas giants were higher for more metal-rich stars, this was drawn first with iron abundance, but because it was assumed to scale with the metal mass fraction. Still, we know that the metal mass fraction is dominated by other abundant elements, and it's computed with all the elements heavier than helium. So, for example, if we look at the abundances of the solar atmosphere, I've highlighted there. So some of the elements that contribute the most, like carbon and oxygen, and also magnesium, silicon, and iron, is also pretty high, pretty abundant and heavy. But still, the carbon and oxygen abundance is so high that they contribute more to the mass fraction. Regarding the models of formation of exoplanets, there are like two big categories: co-accretion and gravitational disk instability. To try to draw where the limits of these models are, I've taken the references for planetesimal formation in disk in co-accretion in blue, planetesimal formation and then formation of planets increasing the mass in these planetesimals, and also to do the limits for the gravitational disinstability. We can look at LAMOST simulations. Of course, these simulations produce protoplanet giants, protoplanets. So maybe to constrain more or less the minimum mass of these systems, we can also check the observational studies like Schlauffmann 2018. So this is the picture, and we want to know if all of our planets fit in this picture, or if we have systems that are not explained by current models. So to do that, we took all confirmed and candidate exoplanets from the exoplanet and .eu archive and NASA exoplanet archive, selecting to have relative errors in mass and radius lower than 20%, and we cross-match this data set with the 3 galactic surveys, GALA, Gaia-ISO, and APOGEE, making sure again that the parameters that define the stars had low enough error, and paying attention to do a subselection of the stars to make sure that the three surveys agree between each other for the common stars. So after doing this, we pay attention to the abundances, and the abundances that we use from these 3 surveys are oxygen, carbon, iron, silicon, and magnesium because of availability and importance in the context of the planet formation and the stellar abundances. And the formula we use to compute it is the usual formula, which needs the hydrogen mass fraction, which we assume to take as the solar one. It also needs the atomic weights of the species, the number densities, and the abundance expressed in the bracket notation. So once we have computed the metal mass fraction for all these hosts, and we have cross-matched the catalogs, we have a sample of 1,349 systems. If we compare them showing the surface gravity and the effective temperature, if we compare them to evolutionary tracks, we can see that they are mainly main sequence stars. We have also a few subgiants and giant stars in our dataset. And I can also tell you that all of them are within a sphere of 1.5 radii of kiloparsecs radii from the sun, with the sun at the center. So they are distributed all around the sky, but mostly focused in the Kepler field. So just briefly highlight that this is where future missions that are to come are important, because all our sample comes from a very narrow place in the sky, and we have many possible targets that we could analyze to get the abundances. So the red dots are the final targets that we took in our data set, and the black dots were the ones that we couldn't cross-match with the galactic surveys, or we didn't find all the abundances in the galactic surveys. So there are still many systems that are not chemically characterized that can be studied. For example, I'm going to make a little bit of advertisement here. Foremost is going to take many of those systems and characterize them in the south hemisphere. About the planets themselves, these are 1,800 planets. A couple of them have measurements of radii and mass. Most of them have only measurement of the radius of the planet, as I'm showing the histograms. I mean, a couple of them have only measurement of the mass of the planet. Most of the hosts that we cross-match are characterized through APOGEE, a couple of them through GALA, and we have 2 systems that are characterized with Gaia-ISO. So if we go back to this theory plot that I was showing before, if I put all these targets there, this is how the picture looks like. okay, the sizes and the symbols have different meanings, but let's keep that for now. And we see that in principle, most of our systems fit very well within the limits drawn from the models. But there are a couple of systems that are too metal poor and small to be explained with characterization or with this instability. So we might think, okay, maybe if we study the CO ratios, for example, if we change them in the theory, we can still form planets thanks to the water ice lines. Maybe these limits can be drawn for lower metallicities, like it was done from the light area to the dark blue area. But still, there are systems with very, very low metallicity. I should look. It would be important to look at the alpha elements or magnesiums. Other works have been seeing these trends in which low metallicity stars have enhanced their alpha or magnesium abundances. We could also think, okay, this is the best data that we have, but maybe the errors is too large, and maybe there is some inconsistency. So maybe we need new data and surveys. In general, what I'm doing now is checking each individual system to try to understand them better. But this is an ongoing work, and I'm reaching my conclusions here. In principle, models can explain most of the systems that we have. A couple of them are not explained by the models, but maybe we need better data to see if this is a problem with the abundance measurements we have, or if we should update the models. Again, I'm checking the systems and working on them right now. So with that, thank you so much, and I accept questions.
Okay, yes, question. Here and
Thank you. Thank you for the interesting talk. The almost last figure, that was a little fast to me. So it is more or less like 90% of the planets formed by core accretion, and maybe 10% by gravitational instability or something like this?
Yes, I mean, at least from the data we have, but there's still many, many more systems that we couldn't cross-match with the galactic systems. But yeah, I don't think it's in the 90-10, but I don't remember exactly the numbers. I should have put them in the slide.
Yes, one has to
yeah,
count the points,
by the look at it, it should be something like that, yeah.
Mm-hmm.
Mm-hmm. Yes?
Thanks for the nice talk, very interesting. So I wanted to ask you, since you are using mostly Kepler stars, what is the criteria you have used to determine that these are real planets, because they don't have radial velocities to be confirmed? Mm-hmm. So did you apply any cut to know that there are real planets there?
I was taking the planets directly from the exoplanet catalogs, so they already have labels about how reliable the detections are. So I took the confirmed ones.
So maybe they are these validated ones from?
Validated ones, and also candidates. I took a couple of them.
Okay. Mm-hmm. So it could be that in reality.
Yeah, it could be, exactly. I should. I'm still checking the systems. Some of the systems are confirmed, strongly confirmed. So some of the systems of the outliers there. So
maybe you can find abundances for some of these ones with Keck, because they were doing follow-up of some of these Kepler targets in the north. And then you can have better abundances.
Okay, maybe, that would be great. Thanks for suggesting.
Yes?
Thanks, very interesting. Do you have abundances of carbon, oxygen, of all these elements from all the surveys?
Yes. I mean, that was one of the criteria I used to select them, like to have the abundance for carbon, oxygen, magnesium, silicon, and iron. If not, they wouldn't be there.
Okay, and have you checked the flux in APOGEE and GALA? Because I looked at abundances, and I think there is no single dwarf, FGK dwarf in GALA that has a C, carbon or oxygen abundance without a flag with warning.
Ah.
All of them have a flag with warning saying that they can
okay.
be although the errors can be small, but they have a warning that the abundance shouldn't be trusted.
Okay, I used the catalogs following the suggestions from the guidelines from each survey. So I used them in the most conservative way. Maybe still they have flags, but thanks to pointing it out, I can check.
Okay, well, yeah.
Yeah, no, just a quick comment about these stars that with super low metallicity, right? I mean, it's great to check from all the abundances and so on, but you know, as somebody that works on the theory in planet formation, it might just be also that we miss something in theory to explain this, right? This is why it is important. It's not only that maybe there's something wrong with the abundances, but also be that our theory is not complete. Just wanted to point that out.
Yes, I tried to say that out loud. Maybe I was too subtle mentioning it.
Okay, I will ask also a question here. So you have the, so to say, okay, well, but here you have only stars with planets, right? Do you have a comparison sample also so that you can check if the if the trend of iron abundance is the same?
We have done that. I didn't show it because at some point I felt like I was stuffing too much things in the talk for 10 minutes. Yeah. But we have compared it just taking again the stars from GALA and APOGEE and trying to cut them in a way that they are covering the same volume in the galaxy as our exoplanet hosts. Maybe, yes, and subselecting them in the same way so they agree between surveys. And we see that for giant planets, the distribution of hosts is more metal rich than this comparison sample that we made out of the surveys. For small planets, it looks like it's slightly higher metallicity too, but it's not that, the separation is not that large. It's not that evident.
Okay, thank you very much. Yeah, I think we end this session about stellar chemical composition here. Thanks again to all speakers. Now it's lunch. Now it's a group picture, and after that, lunch.